whiteboard on the screen. What are the questions?
In the very beginning of the history.
Можно все-таки вопросы показать, а? На слайде. Ну, в смысле, ну, что?
В чате их нет.
Вот таких. В чате. В чате, вопросы чата можно вот показать?
Это чат. Нет существенных вопросов.
В начале вроде не было вопросов никаких общих.
Подожди, там был какой-то про 5 сигма, еще что-то такое было.
Maybe we start doing the researches.
Okay, let's start the discussion. I would say that
You know to start? As a discussion leader, you are.
yeah.
You are the master.
Yeah.
So may I ask you some questions?
Yes.
Yeah, thank you.
Is it some experimental evidence for a change of baryonic charge of the universe in process of its evolution?
No.
So the question of baryogenesis is not experimentally motivated.
It is, it is motivated by the fact that, well, we know that we always produce the same amount of matter and antimatter in collisions, okay? And naturally we expect, say, that we start with some symmetric plasma or symmetric situation anyway, without any baryonic charge, okay? And if we look at for example, inflationary beginning of the universe, then that's the situation, because as Stravinsky explained, that within this paradigm, we enter the hot Big Bang stage with universe completely empty. Okay, so the visible part of the universe is empty. There are no any charge, any particles at all. Okay, so in this case, you need some mechanism to produce all particles, including extra baryons. Okay. But you're absolutely right. There are no direct evidence that some process of production baryons or destruction of antibaryons operated in the early universe. And also we know that we need this baryon asymmetry, at least by the time of Big Bang interaction. But where it operated, I mean, before, whether it was in electronic scale or before or after, we don't know.
Behind you.
Great. Definitely proven that all redshifts of the galaxies are due to the expansion of the universe. Definitely proven. No, of course not. Of course, I mean, it's not correct that all the redshifts of the galaxies due to expansion of the universe, because there are also movements of galaxies. Okay, like here, I mean, Milky Way belongs to the local group, and we have Milky Way in the large galaxies. We have Milky Way and Triangle, and also no, small galaxies like Magellanic Clouds, But we move around some general common center. Okay, so we have the local velocities also, and when you measure the redshift, you measure also some contribution due to local velocities of the source and also of the observer. The observer is Milky Way.
Perspective from peculiar modes and the expansion mode.
Well, it depends on the
See
distance.
different
It depends on the distance to the galaxy. If that galaxy is at the, at the distance of gigaparsec, you can, well, for this measurement, you can make this small contribution. But still, it's 10 to the minus 3. Okay, so this is the 10 to minus 3 effect, just because of our motion. So yeah, for example, if you discuss the nearby galaxies, it's 100% important. For example, maybe it's because the historical measurement of the Hubble by the Hubble constant gave some 500.
No, confusion is possible.
Well, confusion is also possible. Yeah, but I mean, in this sense, it's a correct question. No, it's not just the expansion. It's also contribution of the local velocities. Why there is a belief that the installations come from the high energy primordial universe? Well, they are correlated. They at least during the hot Big Bang stage, each time we observe some part of the universe, some parts of the universe which were not in causal connection before that. And still we observe that the temperature is the same, and these patterns, I mean, this when we discuss it in terms of perturbations, these perturbations are highly correlated. And to make this correlation, you need some more earlier stage to do this. Okay, so that's why we believe that they are, came from some earlier part of the universe, or earlier stage of the universe. And in case of inflationary paradigm, it is perturbation. It is actually perturbations of the inflaton, which is most possibly responsible for this, correlations and all this anisotropies. Which is the physical origin of the initial conditions necessary for. Maybe Alexey Alexandrovich.
Да.
Maybe you answer the third question. Okay, the third question. Which are physical origins or reasons of the initial conditions necessary for inflation?
No, okay.
It's a very interesting subject by itself. Okay, we can.
Okay. So the statement, simple statement, it was just as I made in my talk, that if we assume the most symmetric initial conditions, namely adiabatic vacuum for the range, not for all Fourier modes, but for observable range, and actually much more. So we assume this simplest hypothesis, and we obtain the correct absorbed spectrum. Okay, so another alternative, maybe if we assume something else. Is it possible? The point is that without inflation, the advantage of inflation that we have, that we make assumptions about things which are in causal connections. The alternative, without inflation, we only can say that these were some initial conditions. Okay. But physical origin, I would say, in the sense that this assumption is internally self-consistent. That it's not possible to have inflation if you have, say, if you have initially large number of particles, because this will be tracing back in time, that will be in contradiction with inflation. So I will say once more, so I summarize that the assumption that we use adiabatic initial conditions, adiabatic vacuum, that produces the correct observation spectrum, and consideration of some other possible initial conditions, say some particles at some scales we have from observations we have upper limits on this particles, on this the possible particles on non-vacuum initial state, which are rather stringent.
Okay, thank you.
Okay, Dima, may I also add to your answer on the first question?
Yes, please.
Because let me remind you that the whole words of the expansion of the universe actually is simply words which describe the observational fact that indeed at sufficiently large scales that we have isotropic Hubble expansion. So the words expansion of the universe are in some sense only words. What we actually see is just what you said. We have Hubble expansion plus indeed peculiar velocities which are small at large scales. These peculiar velocities are of the order not exceeding few hundred kilometers per second, and so they are becomes less when the Hubble velocity at scales exceeding approximately 10 megaparsecs. So the words about expansion of the universe are simply words, because once more the actual fact, what is seen is with Hubble velocities, and by the way, the trivial consequences of the fact that these velocities are proportional to the first power of radius of distance is just the proof that actually this expansion is homogeneous in the sense that it will be seen essentially the same from any other observer.
Yes. Thank you. The first question: what is the most feasible observational proof of a black hole? Konstantin, are you with us? If not, I mean, there are two speakers on the black hole.
Okay.
Yeah.
It's an interesting question. In some sense, also, it's let us say a philosophical one. It's just like historical introduction to answer this question. Early people are saying that is critical issue is the presence of event horizon. So if there is event, but how to detect event horizon? Well, because you have, in this case, you have infinite redshift near event horizon. So now, its life is, let us say, in some sense, simpler. So for instance, we know for the galactic center or M87, black hole model predict the presence of shadow. Is it possible to get a shadow with another model? Yes, it's possible. There is a boson stars. They could reconstruct boson scalar fields, boson fields may provide a model just to reconstruct the same shadow. Is it possible? It's possible. But for me, it's not, let us say, from a statistical point of view, it's not attractive. It's not attractive. So this model is, in some sense. Second issue, you have to keep in mind that just to, let us say, to explain dark matter and dark energy models with gravity effects, people introduce some alternative model of gravity, and they have different theories of gravity in different objects. So, and now also very important, let us say, methodological conclusion from observational data. In the galactic center, we have the same general relativity like in our solar system, observational fact, not theoretical, but observational fact. So in this case, it's like confirmation of universality of gravity theory, as Newton said. Gravity theory is universal elsewhere. So, and also important thing that is trajectories of bright stars in the future. So not only as first post-Newtonian corrections, since it was found that extended mass distribution is rather small in comparison with mass of black hole itself. In this case, we could expect to find, let us say, confirmation of general relativity prediction in the strong gravitational field approximation, not like first post-Newtonian correction. So, but again, it's still, so there is a room, I told you about shadows. So boson stars could provide the same shadow as black holes. But you see, there are still these two models. But important thing that shadows, not shadows, because we cannot observe darkness. Basically, astronomers detect not shadows, but bright rings. But theory is saying that you have, that is, bright rings is a boundary of darkness. But bright rings may be formed not only with black hole concept. In some sense, it's again, it's action of gravitational lensing. So if there is a gravitational lensing, if you have some, let us say, gravity source, in this case, it's like Einstein-Wilson rings. Again, it may be formed. So there are a couple of alternative theories, but there are some, let us say, other constraints in this model.
But generally, it's not specific, strictly speaking, for black holes only.
Yes. But everything is consistent with, let us say, standard concept. So conservative standard concept black hole is consistent with observation. But also about first and second question, it's just historical, let us say, remarks about this. You know, about expansion. First, it's probably just if you will slightly change this question and all redshift of the distant galaxy. Probably it's in this case it won't be, but from technical point of view, it's not very easy, a simple question for astronomers to confirm, to let us say, to find redshift. Because it's very often it's only one spectral one.
Really?
For distant galaxies, alpha, Lyman alpha 1, only one very often for distant.
I
And
mean,
this
all these evidences for, galaxies at redshift 10 or
Yeah, well, for this it's let us say spectroscopies are saying that is you have to be very careful. But again, it's very similar conclusion. Everything is consistent with standard paradigm. Everything is consistent, no volition. But sometimes, let us say, skeptical people are saying, look, there are two different galaxies or quasar and galaxy is different redshift by they look like in direction. I saw this publication with respectable journals, so it's very questionable. Of course, it's probably, but there are many mysterious things, and also about anisotropy. You know, it's. I remember that. You know, again about history of this issue. You know, Big Bang concept, not concept, but coined these words, was introduced by Fred Hoyle, like joke, big joke. But Gamow disliked this Big Bang. In interview, he said, "I never use Big Bang because it's let us say high energy universe model." But also you have to keep in mind that alternative of Big Bang cosmology was steady state universe model. Steady state was introduced by Hoyle, Burbidge, and Narlikar. And one of the last their publication series monograph on the issue to explain everything was published only 20 years ago, before double Newman. They said, we explain everything with steady state. But they are not amateurs, they are famous astronomers. Narlikar is still alive, as I know, but Burbidge and Hoyle, unfortunately, they died. But they said, we could explain everything.
Nobody believes them.
No, but it's question before this date, before WMF, they are saying you could check it, you could find in these books in library. So, but criticism was very useful, just to understand all arguments of both sides. And for instance, if you probably Feynman lectures on gravitation. It was published 50 years. It was written 50 years ago, published much later. But Feynman explained two alternatives: Big Bang and steady state is the real alternative.
Okay. Many thanks for this illuminating answers for these questions. And the next one, which could be possible cosmological implications of extra dimensions?
Seems rather to be for the next session, because nobody touched even extra dimensions in all
Yes.
talks we had.
Yes. Naturally, I mean, if the extra dimensions are small or open up at high energies, that of course naturally we would expect that we change the early time cosmology. Okay, but also there are models where the parallel brain can touch us, and this is the initial stage of the very early universe from our point of view, and like inflation or beginning of this Big Bang theory. People discuss these issues, but I'm not sure that they're very accurate in descriptions of the observables within this framework. But I'm not sure about the general cosmological implications. Right there.
Maybe
Yes.
somebody from participants.
Okay, Dim.
Yes, please.
Actually, once more, it's always better to speak not about explanations, but as I said, about predictions. What can be an interesting consequences not of all models with compactified dimensions, but with models of brain type, that in these models, in the models in which matter, usual matter is on the brain and gravitons are in the bulk, then it's rather natural to have the difference between the velocity of gravitational waves and the velocity of light in vacuum. And indeed, the fact that we have from our observations such a strong constraint for the possible difference less than 10 in power of minus 15, it makes very strong restrictions, or of course not on all models, but on some models.
You mean observation of gravitational waves from this binary?
Exactly.
Yeah, but it's not physics. Sorry, it's not cosmological implications, it's physical implications. Yes, okay, I agree.
В чате там есть?
Там 23 в чате.
Да большая часть это мусор.
Can I ask a question?
Yes, please.
Dima, maybe you can give some comments about the stage before the inflation.
Before the inflation.
Yes.
Look,
Well,
the inflation
do
itself is looks like, you know, it's something which erased everything which was before the inflation. Okay, after that the universe is empty. So I mean, it's very difficult to imagine some not specially tuned situation where after inflation you still have something to, you know, to measure, something to observe, and to check that there was some stage before the inflation. Inflation is like erasing of everything. Do you
Okay,
agree?
So it's for philosophers.
let me make
Question for philosophers.
let me make more concrete statements. There exists a number of possibilities which actually was already mentioned, I think, 20 years ago. So one possibility is bounds, and actually one should not go too far to obtain a bounce. It's simply sufficient, perhaps say, a massive scalar field and positive special curvature. The second possibility, which is naturally realized in most existing models of inflation, but before inflation there was a generic anisotropic singularity with curvature much exceeding that during inflation. And the third possibility, which I already mentioned it in my talk at the quantum gravity symposium, the second quantum gravity symposium, that before inflation, our universe was not was actually only a part of something much more complicated, or what is now called multiverse. So I would say I think that this is the three main, I would say, the most interesting possibilities of what was before inflation. Is it possible to distinguish them? Once more, it just I would say that the just in the same type of answer, say to the fourth equation, it is better not to check just this fact, is it black hole or not, but to check the underlying theory. So if let's say unified quantum field theory which can be tested by some other experiments is presented, then okay, we shall answer the question what can be pair for inflation.
Yeah, but it's not direct. In any sense, it's not even indirect observation evidence for this type of stage, I would say. Even this discussion of the curvature, okay, again, even you have this bounce in cosmology. Still, you need this inflationary-like stage after the bounce, okay?
Yes, of course.
And so this curvature should be again can be again be very, very small. And I would say that this is only actually very robust predictions of inflationary stage, that if the curvature should be exponentially small.
No, well, once more, if you use inflation and then you just can revert this argument. So even if the curvature is very small now, but if you have sufficiently long stage of inflation, it was large at some moment in the past.
Yes. Okay.
May I ask
Yes,
one
please.
more naive question? As far as I understand, the inflation is considered as a classical process when the scale, spatial scale, rapidly evolves from some small scale to the large scale in course of exponential inflation. Were there any attempts to quantize this process? So that there was a quantum transition of scale as a quantized variable from some small value.
It is done. Actually, it is done. Actually, even first in the simplest case, it is done when we quantize perturbation potentially, and it was done in the so-called stochastic inflation. It can be shown that this scale factor is in fact the sum of all this quantum modes. So so in some approximation, okay, in some approximation, actually in one more approximation, we can consider inflation as quantum. In fact, I even said in my talk that the universe, according to inflationary scenario, the universe is quantum is even at present. So perturbations are quantum, and actually the scale factor itself is quantum, but its non-commuting part is fantastically small as compared. So as to its main value. So it can be considered as that's why it can be considered as a classical but stochastic quantity.
Thank you.
Other questions?
Maybe from Zoom.
Finish.
Well, may I ask the last question? Inspired by the very first question raised at the discussion session, we know for sure that there is a baryonic asymmetry in the universe. What can be said about leptonic asymmetry? Because we have, well, some uncertainty with relic neutrinos. We don't know their composition, whether they have.
Can you
positive or
speak
negative.
close to the microphone? It is not possible to hear from Zoom.
Oh, well, I have to repeat my question. We know for sure that there is a baryonic asymmetry in the universe. What can be said about leptonic asymmetry? Because there is a component associated with relic neutrinos whose composition is not known, as far as I understand. Can you comment on this?
Yes. Well, actually, no, as I mentioned during my talk, if the temperature exceeded 100 GeV, then the Sphalerons transition interchange the baryonic and the leptonic charges. Okay, so from this process, you expect that the asymmetry in the leptonic sector should be at least at the level of 10 to minus 10. Okay, at the same level, 10 to minus 9. Okay, the same level as we have in the baryonic sector. And obviously, it's in the sector of neutrinos. Okay, so it's the difference between neutrinos and antineutrinos. Okay. However, you can ask this question, phenologically, which number is allowed by observables, by observations, and here is the answer actually comes from nuclear synthesis, where people constrain this asymmetry at the level of 10 to minus 2. Okay, and for example, these anomalous observations of new helium abundances and deuterium abundances indicate that well, if it's if you try to explain it within the paradigm of just new neutrinos, then you need to introduce some asymmetry in this neutrino sector, and the asymmetry should be at the level of 10 to minus 2. Okay, so not larger, but can be smaller. Okay, you may ask how you can produce the leptonic asymmetry after electroweak symmetry breaking, and there are models of this type. For example, NUMSM can do this. Okay, but the asymmetry in leptonic sector should be smaller than 10 to minus 2.
Thanks.
Other questions or comments? If not,
We live in apart from
Your conclusion now.
conclusion. Well, it's actually, I would say it's actually very interesting topics we discussed during the morning session, and mostly they're interesting because of enormous progress in from experimental point of view. With observations of many interesting things in cosmology and astrophysics, well, it's a very spectacular thing we have, and we expect more. Okay. So thank you. Thanks all of the speakers and all of the people here in the audience and in Zoom. Many thanks.
Now we'll have a break.